So in last class, we have seen when we see the energy structure, okay, of a electron in a periodic crystal, okay. So periodicity of crystal or periodicity of potential give rise to bands, okay. So we have a allowed energies, and then we have a gap, okay, and then we again bands, okay. So the origin of bands in solid is because of presence of periodic potential, okay. Now today what we are going to see, we are going to see ek relations, okay. So we know, yes. Ah,
Previous day, we see that in increasing of alpha A, the bands get wider.
yes.
सर इसका लॉजिक क्या है? मैं ये एक्सपेरिमेंटल
बताएंगे बताएंगे इसका लॉजिक बताएंगे जब मैं बताऊंगा आपको पूरा बॉन्ड फॉर्मेशन कैसा होता है वो बताऊंगा, ठीक है। तो वैसे तो आपको कुछ तो आपको पढ़ा हुआ होगा कि जो आउटर 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 जो होते हैं, आउटर जो ऑर्बिट्स होते हैं, ओके, वो ज्यादा परटर्ब्ड होते हैं, ओके। जो आउटर ऑर्बिट्स होते हैं वो ज्यादा परटर्ब्ड होते हैं, तो जो बैंड्स ग्रो होते हैं वो आउटर 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 साइड में ज्यादा बैंड ग्रो होते हैं, ओके। सो व्हेन आई विल सी क्लासिफिकेशन ऑफ मेटल इंसुलेटर सेमीकंडक्टर, दैट टाइम आई विल डिस्कस दिस थिंग्स अगेन, ओके। So today just let me discuss this ek relation, okay. So what is ek relation? So we know that when we have, if I draw the k versus e curve, okay, so we know the free particle, we have h cut square k square by 2m, okay, and we can have this zero energy also, okay. But when we are in crystal, okay, so at the moment I am discussing one electron in a crystal in lattice potential. Yesterday Sultan was asking, sir, why are we not discussing the case when, because there is a lot of electrons in the crystal, so why you are taking one electron, okay. So you may be knowing when you do your particle in box, okay, that time also when you want to calculate energy levels, that time also you consider only one particle, okay, not even their charge, okay. You consider a particle who has a mass m, and you apply boundary conditions, potential, and you get the an energy diagram, okay. And then comes later case, once you know the energy spectrum, okay, available energy, what are the energy levels are available, then you can bring more electrons, okay, and you can fill the states, whether it's a fermion, whether bosons, the charge, that comes later, okay. So first, the like we do in our particle in a box, okay, we have a one particle, and we have a boundaries, and we are applying boundary conditions, solving Schrodinger equation, and we are calculating the structure, okay. Similarly we have done for electron, okay, one electron when it is in a periodic crystal, okay, so it has a allowed energy range, and there is a forwarding gaps, okay. Now I want to draw the energy ek relations for your particle, okay. So now difference, what we see, the ek diagram for a particle in a crystal. So first thing, we don't have a continuous k values, okay. So we have a k values, we all know this pi by a, okay, 2 pi by a, 3 pi by a, okay, minus pi by a, okay, minus 2 pi by a, okay. I can draw one more line here if it is visible, okay, okay. So minus 3 pi by a, okay. Now here our curve starts from 0, e is equal to 0, okay. So but you know, whenever you restrict your particle, like in your particle box, okay, you don't have a this zero energy, okay. So you don't start from 0, okay. So when you increase the k, okay, now you have a parabola type of curve here, okay. So here we don't have exact parabola. What happens, my curve starts, okay, my this is my e energy, and what happens at the boundaries, this e curve become parallel, okay. Why it become parallel? Okay, so we know at boundaries k equal to n pi by a. Okay, for example, say k equal to pi by a. So k equal to pi by a, what happens? My k is 2 pi by lambda, and this is my pi by a. Okay, so pi by cancel. Okay, so I get lambda equal to 2 lambda equals to 2a. Okay, so when you have lambda equals to 2a, that means what? One thing what is happening, one thing is it is happening that you have a diffraction condition. Okay, we know what is the diffraction condition. So diffraction condition is your 2d sine theta equal to and lambda or lambda you say first order. Okay, so if it is a perpendicular incidence, okay, then you have 2d equals to lambda. Okay, so similarly here also diffraction condition get satisfies. Okay, so what it happens, your electron get diffracted. Okay, one thing. Second thing is there, because they are forming standing waves. Okay, so we know the velocity. What is the velocity? Velocity is vg. Okay, so vg is what? D omega by dk, and this we can write 1 upon h cut d upon dk. Okay, so at the boundaries your velocity is also zero. So velocity is also zero, that means your ek diagram should not have any slope, should have parallel. Okay, so what happened at the boundaries, this curve becomes parallel. Okay, now because of this diffraction condition, they form standing waves if this condition is satisfied. Okay, if this electron have this much energy, this much k or this much energy, okay, then they form standing waves. Okay, and because of this standing waves, the here we have get discontinuity, and there is a orbital gaps. Okay, so in physics wise, if you see why there is band gap in the system, because of this diffraction conditions. Okay, so this is my first thing, and second, again there will be gap, and then it will start again, and this become like this. Okay, and similarly there are discontinuities at k equal to n equal to pi by a, 2 pi by 3 pi by a. So we'll get this kind of graph. Okay, so this is the one thing. And you have to remember one more thing, that whenever you have a your band structure, okay, so band structure always follows periodic crystals. Okay, in a periodic crystal, your band diagram always follows inversion symmetry, that is ek equal to ek. Okay, so along with this inversion symmetry, this is called inversion symmetry. Inversion symmetry. Inversion symmetry. And also your band diagram follows the translation symmetry. Translation symmetry matlab kya hai? If you are E K, okay, so E K plus G, that will be also equal to your E K. Okay, so where G is what? Where G is your uh, reciprocal lattice vector, reciprocal lattice vector. Okay, which is given by what? G equal to 2 pi by a. Okay, that means if you translate your energy, okay, from k to k plus 2 pi by a of 3 pi by a, 2 pi by a, 4 pi by a. Okay, so that value will be the same. Okay, that is a translation symmetry. Okay, and also your ek energy diagram, ek also follows, okay, follows rotational 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 symmetry of your crystal. Okay, that thing we don't need here. Okay, we'll discuss later when we discuss this ferroelectric properties. So ek follows rotational symmetry of crystal. Okay, so rotational symmetries of crystal. Okay, now we have this diagram from ek. Okay, now it should follow in inverted symmetry. So in this side also you get same kind of graph. Okay, so here this we have, and you get this one again. So this
सर सर मुझे एक बार पाई बाई ए वाली डिसकंटिन्यूटी फिर से एक्सप्लेन कर देंगे सर?
ये वाली पाई बाई ए वाली
Yes, sir.
ओके सो जब यहाँ पर पाई बाई ए आएगा, ओके पाई बाई ए आएगा, इसका मतलब क्या बन जाएगा, स्टैंडिंग वेव बन जाएगी ना।
Yes, sir.
स्टैंडिंग वेव बन जाएगी मतलब कुछ मूवमेंट है ही नहीं, जैसा मैंने फर्स्ट आपको फोरम किस्ट बता रहा था। तो जब बता रहा स्टैंडिंग वेव है तो एनर्जी प्रोपोगेशन है ही नहीं, एनर्जी स्टेट है ही नहीं वहां पे। ओके
Yes, sir.
so because they are getting diffraction taking place, okay, that point we don't have any energy, okay, so there is a break, so a break hai, and then we start again for second band, okay. So this is your what first band, so this is your first band. Similarly this is your second band and so on, okay. So when we, so there are many ways scheme to represent your ek relations, okay. So generally when we want to do in general simple presentation of E and K, so then we represent ek relation in this way, okay. That is called your extended Jones scheme. So this type of ek relation, this type of ek relations are called extended Jones scheme, okay. Now when you see literature or you see some publications, okay, you don't see the ek diagram of solids in this form, okay. So when you see, so I'm erasing this one, huh? So when you see the literature, generally your ek diagrams, okay, your ek diagrams are shown in reduced zone scheme, okay. So what is reduced zone scheme? So reduced zone scheme. So now here we have a first band, okay, first billion zone, first band, second billion zone, second band, third billion zone, third billion zone, okay. Now we have vector k, okay. It has a translation symmetry, okay. So if we change k by k plus 2 pi by a, that is same thing, okay. So what we can do actually, we can bring this all the bands, okay, instead of going outside of this first billion zone, okay, we can bring all these bands in first billion zone, okay. So how to do? So I told you ek diagrams has this translation symmetry, okay. So if I want to draw this my reduce zone scheme, reduce का मतलब है कि हमको zone को reduce करना है, so I have to bring this one, okay. So what I will do, simply I will translate this by 2 pi by a, okay. So if I translate this curve by 2 pi by a, so it will come, how it will come here, 1, it will come here, okay. So what will happen, I have this my scheme here. I have a pi by a, I have minus pi by a, okay. So now I have a first band, okay. Now if I translate this curve inside the first zone, okay, so it will become like this, okay. Similarly if I translate, I'm translating this here, okay, this arrow is showing here, and I'm translating this here, okay. So if I translate this one, so this become this type of graph. Similarly if I translate this type of this curve, okay, here, so what will become, this will become this type of graph, okay. So whenever you see literature, always you will find your ek diagram, ek curve, okay, they are shown in reduced zone scheme, okay. Now this presentation and this presentation is both are same, okay. I will tell you why. Shall I rub this one?
Yes, sir. सर एक और डाउट था सर, सर इसमें आपने k का वैल्यू सॉरी e का वैल्यू 0 नहीं लिया है,
हाँ
डायग्राम कंसीडर करते हो? यस सर,
जीरो नहीं लेते ना, क्योंकि आपको पार्टिकल तो बाउंड है ना, क्वांटम
यस सर,
बाउंड है ना, ओके
ओके ओके सर.
so now I will explain this graph, okay. So okay, इसको तो रहना चाहिए तो कोई बात नहीं, चलो हटा देते हैं. Now we are telling that we this vector is our k vector progressive vector, okay, we can translate by 2 pi by a, okay. So suppose I have a graph, this one graph, okay. So now I'm drawing this type of graph. I'm not showing this for just for understanding. I'm not showing here gap only gap. Okay, so this is my graph. Okay, E versus K graph. Okay, so say this is 0. Okay, and say this is pi by a. This is my 2 pi by a. Okay, and say this is my 3 pi by a. Okay, and here minus pi by a. Okay, and again we have 2 pi by a. Okay, now since they have a translation symmetry, okay, so I can plot the same graph. Okay, same graph like this also.
Sir,
Ah,
in the right hand side picture,
ah. मैंने
the third curve
हाँ,
in the right hand side picture,
yes.
the third curve will be downwards open.
Just let me check. Okay, yeah, she should be downwards. Yes, correct. I made it wrongly. Okay, so this should be downward. Yes, thank you. Okay, now similarly I can translate this from here also, this band diagram, this. Okay, I can translate my parabola by 2 pi by a. Okay, now if you carefully look this graph. Okay, so carefully you have this portion. Okay, similarly you have this portion. Okay, now you have this portion. Okay, you have this portions. Okay, and similarly if you keep on drawing, okay, you have this portions. Okay, and you have this portions. Okay, but what is happening? Okay, only there is no gap. Okay, because I told you, I'm just for explaining, I'm drawing like this. Okay, so if there is a periodic potential, this periodic potential, what will happen? What will do? It will disturb the system. Okay, and there will be origin of their gap will start originating. Okay, so there will be gaps between the bands. Okay, so these presentations and this presentation are same. Okay, but in literature generally, because whenever you go outside, that just a repetition of this bands. Okay, so generally when you see literature, they show you reduced zone scheme. Okay, and along with this reduced zone scheme, okay, you have one more type of scheme. Okay, that is called periodic zone scheme. That is rarely used. That is called periodic zone scheme. Okay, so that is actually never used. Okay, so periodic or repeated is called repeated zone scheme also. Periodic or repeated zone scheme. Okay, so in repeated zone scheme, what we do? Okay, whatever we have in our first billion zone. Okay, whatever we have our first billion zone, that energy curve we just translate. Okay, so suppose we have this one. Okay, so this is pi by a, this is 2 pi by a, this is 3 pi by a. Okay, this is minus pi by a, 2 pi by a. Okay, so now what I'll do, so I have this curve here. Okay, now I will simply translate this curve. Okay, so now what will become? This become this type of curves. Okay, so this will repeat. Similarly, this will also repeat. Okay, so this is, we have a curve of this type of curve. So these bands will repeat. Okay, so this type of presentation is called your repeated zone schemes. Okay, only what we can do, so we can find from this this type of representation. So generally our free particle this representation is parabola. So here after it's showing it's also parabola, except that means your particle in crystal also it behaves like a free particle, only except the behavior is different at the boundaries. Okay, because boundaries there's a discontinuity, otherwise near the boundaries only it behave differently. Okay, so that is the meaning of this curve, but we don't use this one. Okay, always you see literature, that is actual band diagrams are very complicated. Okay, but this is some simplest representation. So whenever you see literature, you always find your band diagrams are sketched in reduced zone scheme. Okay, so this was about presentation of billion zones. Okay, so this is the first billion zone from pi by 2 minus pi by a, and I told you yesterday in within pi by, if when k is between pi by a and minus pi by a, then we have a total n states. Okay, and the number of lattice points. Okay, so here although I'm showing this is a continuous curve, okay, this is not a continuous curve, okay, there are only n by 2 states on this side, n by 2 states on this side, okay. So k has some values here, some very small, because these values are very small, okay, okay. That's why, and that's why they look like a continuous. Actually this curve is not continuous, these are points here, okay. These are very small distance, okay. That's why it's looking like a thing, okay. Now when you, now of your exam point of view, okay, so if you see your exam, in your exam mainly questions which come from band theory, they are based on your effective mass and your ek dispersion relations, okay. So let us solve today some problem, okay. First let me discuss what is effective mass, and we will solve some problem today from your exams, okay. So put the heading now, effective mass, okay. Okay, so effective mass means how your particle or electron respond to external force in the crystal, okay, when it is free, okay, and when it is in the crystal, okay. So generally your effective mass, okay, in the crystal is different than your free electron mass. Let me derive the expression for your effective mass. So we know what, we can start with the velocity. We know the electron velocity in crystal, okay. So electron velocity in crystal, okay, is equal to what, group velocity Vg d omega by dk, and I can also write this d omega by dk is 1 upon h cut d e upon dk, okay. Now my aim is to calculate what, my aim is to calculate force, like force, okay. So I know what is force is basically f by m, okay. So it's f by m, okay. Now I know the relation between P and H, P and K. P is H cut K. Okay. So if I want force dP upon dt, so I can, what I can write H cut dk upon dt. Okay. So I can put so okay, so d by dt, okay. Now I want this, my acceleration, okay. So my acceleration will be what, a equals to one is definition, this one, another is what, dvg upon dt, okay. So this will give me 1 upon h cut de by dt and dk upon dt. Am I right? Correct है क्या?
through dt by dq.
अब ठीक है? Okay, so dk by dt, okay. Now
Yes, sir.
this a will be what, 1 upon h cut. If I put the value from dk by dt in this expression, okay, so that will be 1 upon h cut dp upon dt. So this become 1 upon h cut square d2e upon dk square dp upon dt, okay. And if I write again this one, दिखा है ना, a 1 upon h cut square
Sir,
d2e,
can you please explain A equal to the first line? What happened there?
this one,
No, in the right hand side, the first line.
this dv by dt na, this
Yeah,
velocity.
dA by dt. That is ddt of dk, right?
So dvg by dt, to differentiate this equation, okay. So if you differentiate this one, they become d by dk2, and we have to do k once again, okay. So dk
Oh,
by dt,
that's dk2. Okay.
okay. So this one, now if we do it here, okay, again, so I have 1 upon h cut square d2e by dk, dp upon dt is force, okay. So if I compare these two equations, okay, okay, this is a force, okay, we have force, acceleration, okay. That means 1 upon m star, okay, is equal to what, is equal to 1 upon h cut square d2e upon dk square, okay. So I can write this as a m star will be what? Your h cut square. This is the well-known relation to you, okay? That dk square, okay? So this is your effective mass formula, okay, in one dimension, okay? In general, your m depends on directions also. Your effective mass is a tensor quantity, okay? So it has a 9 component, okay? mx and x, mxs, mx, myy, mzz, okay? So we'll see that when we'll discuss this thing, okay? So this is the in one dimension your effective mass formula. So that means shows your mass depends on the shape structure of your energy band, okay? How your energy band E varies with K, okay? So let me draw some curve. So इसको रब करते हैं क्या?
हाँ सर.
Yes, sir.
So okay, इसको भी रब कर देता हूँ ना. So now suppose I have this is my energy versus K curve, okay? So one more thing here I forgot to tell, this m star is equal to h cut square, okay, d2e upon dk square, okay? So if you have free particle, for free particle we can write h cut square k square by 2m, okay? And if I calculate d2e upon dk2, okay, for this one, so it will come h cut square by 2m, okay, then will 2k and 2, okay, so 2, okay. So if I put these values here, h cut square upon h cut square m, okay, this is free particle, the free particle m naught, okay. So for free particle effective mass is equal to free particle mass, okay. Now we have seen our, I'm only drawing first band, okay. So this is pi by a, this is my minus pi by a, okay. This is my ek relations, okay. Now I want to plot variation of k with variation of effective mass with k, okay. So how can I do this? So this is ek curve, okay. Now my effective mass is what? H cut d2e by dk, okay. That means I want derivative, okay. So if I take derivative of this graph, okay, that will be d by dk, okay. So I know what is my velocity. Velocity is 1 upon h cut de by dk, okay. So if I take differentiation of this graph, that will give me what? That will give me de by dk, okay. That is not that will be same like a vg, okay, because there is only difference of constant, okay. So I can draw. So now these are the parabola, okay. This is a parabola. Parabola means this is k square, okay. Now when you differentiate k square, what will get? So here,
Okay.
so this is your what? This is our here where your velocity is decreasing, okay. These are turning point. Here you have slope k square, free particle like behavior, and from here onwards near to the band boundaries, okay, your your e is this relation is slope is getting decreased and it's becoming 0, okay, here at the boundaries. So if I want to plot this dk or velocity, what will get? Here in this region this will be almost constant because this is k square, this is 2k, so this will be constant, okay. And then you get maximum, and then here your slope is slightly decreasing, okay. So what will happen? Your velocity will decrease and you become 0 at the boundaries, okay. So this will be your d by dk or velocity graph with respect to k, okay. Now my aim is what? My aim is to calculate effective variation of effective mass, okay. So now I want variation of effective mass,
Sir,
effective mass. हाँ
सर ये एकदम फॉल डाउन नहीं होगा जो फॉर्मूला में लिखा है उसमें तो एकदम फॉल डाउन होना चाहिए उस पे।
कौन सा एकदम फॉल डाउन होना चाहिए?
ये जो आपने एकदम से मतलब कि कर्व बना के सॉल्व किया है,
ये वाला
डाउन किया है इसको। यस सर, यस सर। तो ये एकदम से नहीं होगा सर?
एकदम से क्यों होगा? तो स्लोप तो धीरे 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 के बाउंड्रीज पे आके एकदम पैरेलल होता है ना। तो जीरो जो होता है वो एकदम ऐसा नहीं कि यहाँ कैसा हो गया, ऐसा नहीं है। पहले से पैरेलल नहीं आता है वो तो। वो स्लोली स्लोली कम होता है ना स्लोप। ओके, सो नाउ इफ आई प्लॉट दिस ग्राफ m star, okay, so m star क्या है? m star is what? m star is basically your h cut square d2e upon dk square, दिख रहा है ना? So now I have to differentiate this one time more. Okay, so now here we have e is proportional, this is the proportional dk is proportional to k. Here we have a velocity or dk is proportional to k. ओके, सो इफ आई डिफरेंशिएट वन मोर टाइम तो ये क्या हो जाएगा? कांस्टेंट नहीं हो जाएगा?
हाँ सर।
ओके, सो दैट इज v and this is my boundaries. Okay, so what will happen? So here this will be constant. Okay, constant. And what will happen here? Okay, so my and at here we have dk 0, so d2e this is 0, so the mass will become infinite. Okay, so if I plot this graph, so this will be like this. Okay, so this is so because it turning points. Okay, say this is k0 minus k0 and this k0. Okay, so you can write here also this is minus k naught, turning point k naught. Okay, so your mass becomes almost approaches infinite. Okay, and now if you go beyond your dk by this one, then the slope is negative, dk is negative. Okay, so here that means your effective mass will be also negative. Okay, so what will become? So you can draw your curve like this, effective mass curve. Okay, so the effective mass shows your negative. Okay, now what is the meaning of इफेक्ट मास नेगेटिव होने का मतलब क्या है? ओके, तो तुम लोगों ने पढ़ा होगा कैसे मास नेगेटिव क्यों दिखा रहा है?
क्योंकि
See, first of the thing you to understand
कर्वेचर नेगेटिव है क्योंकि d2e by dk square.
हाँ वो तो ठीक है, फिजिकल सिग्निफिकेंस क्या है? व्हाट इज द फिजिकल सिग्निफिकेंस? मास नेगेटिव का मतलब क्या है? सो
वो लोग वहां पे
so यहाँ पे you can see here this happens where? This happens the negative behavior of your mass you see where? When you are near to the boundary. Okay, that is when you are on the top of your bands. Okay, so you have this one. Okay, so when you are top of your band or edge of the band. Okay, then it shows negative character. Okay, or when you or in another way when we will explain the distinction between why some material behave like as insulator and why some are metals, that time also we'll discuss again this thing again a little bit more. So here you can understand whenever it is whenever electron is on the top, these states are filled, and these states are filled like it's happened in insulators or semiconductors. Okay, metal में तो क्या होता है? metal में तो your bands are half filled. Okay, half filled मतलब आप थोड़ा सा एनर्जी लगाओगे तो इलेक्ट्रॉन फुल ऑक्यूपाइड स्टेट से अनऑक्यूपाइड स्टेट पे चला जाएगा. Okay, but when you have a insulator, okay, जहाँ पे सब ये बहुत हैं, then it is very difficult. Okay, so electron, because there is no state to occupy. So what happens here? First we'll discuss here when your k is at the edge, okay, or top of the band, k to pi by pi. At that time, what happens? Scattering takes place. Na? I told you that at k is equal to pi by a, this diffraction happens. Okay, so you are applying some electric field. Okay, now what happening when you are applying some electric field and your electron is coming here and at boundary. Okay, जैसे ही पहले से वो बाउंड्री के पास में ही है. ओके, वो ऑलरेडी टॉप पे ही है. ना आपने थोड़ा सा फोर्स लगाया तो इसका एनर्जी बढ़ाई, एनर्जी बढ़ाने से क्या हुआ, उसका के बढ़ेगा, और के बढ़ते ही के पाई बाई ए हो गया, और जैसे के पाई बाई हो गया that diffraction condition satisfy हो गई, और when there is a diffraction condition get satisfy, what happen, it moves opposite. Okay, so now you are applying force in this direction. Okay, but जो top पे जो इलेक्ट्रॉन है, वो the electrons which reside on the top of the band, okay, they get what, they get deflected in opposite direction, so force in this direction and they're moving in an opposite direction. That means they behave like a holes. Okay, that is called hole like behavior. So you have mass m e. Okay, so you know mass of me is equal to mass of h cut. Okay, so they behave like a, when those you applying force here and they should move here, they move in opposite direction, they behave like they move like a holes. Okay, that's why they have negative mass. Okay, now let me show some problem which is asked in exams. Okay, so can I rub this one?
Yes, sir.
Yes, sir.
So same concept, some problem were asked. हाँ
सर ये ठीक से क्लियर नहीं हुआ सर,
क्या चीज,
ये नेगेटिव
नेगेटिव मास का मतलब क्या है भी, अगर आप फोर्स लगा रहे हो, ओके, जैसे मैं मास पे फोर्स लगा रहा हूँ, तो मेरा मास तो फोर्स की डायरेक्शन में मूव करेगा ना,
यस सर,
और अगर फोर्स की डायरेक्शन मूव अपोजिट मूव कर रहा है, इसका मतलब क्या है, इसका मतलब क्या है, वो मतलब नेगेटिव मास की तरफ बिहेव कर रहा है। ओके, जैसे चार्ज का होता है पॉजिटिव नेगेटिव। ओके, सो एट बाउंड्रीज पे ये खाली हर जगह नहीं होता है, ये टॉप ऑफ द बैंड पे होता है खाली। ओके,
मतलब सर टॉप ऑफ द बैंड होल्स है और इनर
नहीं, होल्स है नहीं, दैट इज डिफरेंट, वो अलग अलग डिस्टिंक्शन है। अभी तो हम देख रहे हैं ना दैट डिफ्रैक्शन कंडीशन सेटिस्फाई हो जा रही है, जैसे हम एनर्जी हम वो ऑलरेडी पाई बाई एक उनका जो के है पाई बाई एक के क्लोज में ही है। जैसे आपने उनको बार्स एक्स्ट्रा एनर्जी दी, उनका के बढ़ गया, के बढ़ते ही वो पाई बाई पहुंच गया, पाई बाई पहुंचते ही क्या हो गया, डिफ्रैक्शन कंडीशन सेटिस्फाई हो गई, डिफ्रैक्शन कंडीशन सेटिस्फाई वो डिफरेंट डायरेक्शन में स्कैटर हो गया। हमेशा नहीं होता ये, उस पर्टिकुलर वैल्यू के लिए आप यहाँ फोर्स लगाया, वो इधर चला गया, थोड़ी सी वैल्यूज की वैल्यू, थोड़ी सी पर्टिकुलर एनर्जी के लिए, ऐसा नहीं कि हमेशा ही घूम रहा है, उल्टा घूम रहा है, समझ रहे चीज को। ओके, वो तो ओनली ऑन द नियर द एजेस, ओके, वो डिफ्लेक्ट हो जाता है। नाउ
सर आपका
sir,
डिफ्रैक्शन ये कंडीशन
sir,
हाँ
near the zone pi by a effective mass तो infinite है ना,
इन्फिनिट मास कहाँ पे इन्फिनिट है?
वो effective mass का जो हम कर्व देखे,
हाँ,
टर्निंग पॉइंट पे
तो हमने
turning point infinite,
तो हमने एग्जैक्टली वहां पे क्या लिया जब हमने प्लॉट नेगेटिव प्लॉट किया। ओके, अप्रोचिंग है ना, अप्रोचिंग, एक्चुअली अगर के इक्वल टू पाई बाय हो जाएगा तो ऑब्वियसली व्हाट हैपन, योर मास शुड बिकम इनफाइनाइट। क्यों होना चाहिए इनफाइनाइट? क्योंकि नाउ सपोज इट्स इंसुलेटर। ओके, इंसुलेटर के लिए क्या करना है, आप ऊपर एनर्जी लेवल ही नहीं है, एनर्जी लेवल ही नहीं है, इसका मतलब आपको बहुत ज्यादा एनर्जी लगाना है। बहुत ज्यादा एनर्जी का मतलब इनफाइनाइट का मतलब ये होता है, इनफाइनाइट का मतलब कि आपको ज्यादा एनर्जी लगाना है, नॉट देयर इज नो बैंड। इसका मतलब ये है कि नाउ व्हाट यू हैव टू गो थ्रू फॉरबिडन गैप। ओके, इनफाइनाइट मास का मतलब क्या है? इनफाइनाइट मास का मतलब ये है कि ना अगर उसको आपको मूव करना है, अगर उसको कंडक्ट इलेक्ट्रॉन को कंडक्ट कराना है, देन यू हैव टू सप्लाई मोर एनर्जी, तभी वो कंडक्ट करेगा। लेकिन मेटल केस में क्या होता है, मेटल केस में इन कंडक्शन बैंड इटसेल्फ, ओके, देयर आर व्हाट इज हैपनिंग, दिस वीडियो इज क्लियर? वीडियो क्लियर है कि नहीं सबके लिए? ओके, सो इन
बीच में
मेटल,
लैग करता है।
हाँ वो थोड़ा इंटरनेट का इशू होगा। सो इन मेटल कंडक्शन बैंड में भी आपके बहुत सारे एनर्जी स्टेट्स हैं, एम्प्टी स्टेट्स हैं, बैंड्स आर हाफ फिल्ड इन सिंपल मेटल, बैंड्स आर हाफ फिल्ड। तो आप उसी बैंड में मूव करेगा तो आपको कम एनर्जी लगानी पड़ेगी। तो मास मतलब मास का ज्यादा नहीं है, मतलब इफेक्ट भी ये कर रहा है, ज्यादा एनर्जी लगा रहा है, पड़ रहा है, दैट मींस देयर मास इज वेरी हाई। ओके, सो नाउ वन क्वेश्चन इज आस्क्ड इन नेट JRF 2016. Okay, So what they're asking, they have given this EK relations. Okay, so EK relations they have given EK is equal to A minus B cos 2Ka. Okay, and they say this Ka varies from 0 to pi. Okay, so now asking in which range इसी में से in which range electron has hole like behavior. ओके, कैसे करोगे इसको?
इफेक्टिव मास निकाल देंगे और जहां जहां नेगेटिव होगा इफेक्टिव मास
हाँ,
वहां मत
तो निकालो इफेक्टिव मास कितना आएगा. आपको ई के रिलेशन दे रखा है. यू हैव फॉर्मूला m कट इज इक्वल टू h कट स्क्वायर d2e अपॉन dk स्क्वायर. ओके, सो कैलकुलेट करो कितना आएगा मास. सो m कट m पर दिख रहा है ना, h कट स्क्वायर. ओके, अपॉन इसको दो बार डिफरेंट कर दो. एक बार करोगे 0 हो गया, माइनस करोगे माइनस बी कॉस के का 2 हो जाएगा, तो 2 हो जाएगा 2b साइन 2k है ना, साइन 2a का फिर करोगे कॉस 2k 4 आएगा, 4b कॉस 2k. ये आ रहा है क्या?
हां सर.
सर ए
तो पाई बाय 4 से पाई बाय 2 तक
ए स्क्वायर पे आएगा, ए स्क्वायर पे आएगा, ए स्क्वायर पे आएगा, कॉस के है ना, ए स्क्वायर आएगा. ठीक है, ओके. नाउ अब ये किस किस के की किस वैल्यू के लिए ये मास नेगेटिव होगा. ओके, सो फॉर दैट यू कैन सी दिस कर्व ना. सो से ऑल ये ऐसे याद करते हो ना, ऑल एसटीसी. यहाँ पे सारे फंक्शन पॉजिटिव हैं, यहाँ पे खाली साइन पॉजिटिव है, साइन यहाँ पे 10, यहाँ पे कॉट. ओके, सो यहाँ पर आपका खाली यहाँ कॉस है, कॉस. ओके, यहाँ पर क्या है आपका कॉस नेगेटिव है. दैट मींस के इफ के इज ग्रेटर देन पाई बाय 2. ओके, सो के सो दैट मींस दिस एंगल 2k, if 2k is greater than pi by 2. Okay, that means k is greater than pi by 4. Okay, whenever k
Yes,
is
sir.
greater than pi by 4, the mass will be negative. Okay, so my range what is my k should be greater than pi by 4. Okay, or or
लेस देन 3 पाई बाय 4.
और 3 by और 3 pi by 2 में भी नेगेटिव होता है. So you can get 3 pi by 4. So this is my range. Okay, so this range your electron will behave like a your hole like behavior. तो और भी प्रॉब्लम्स हैं, तो आसान प्रॉब्लम्स है बहुत ज्यादा, कुछ है नहीं, खाली डिफरेंशिएशन करना है. अब कर दूं इसको मैं.
यस सर.
So now suppose we have E. Okay, this came gate 2016. Gate 2016. Okay, so E is given A K square B Ka4. Okay, so where A is lattice constant, A value is given 2.1 angstrom. Okay, A is also constant whose value is in energy unit 6.3 into 10 raised to power minus 19 joule. Okay, and B is 3.2 into 10 raised to power minus 20 joules. Okay, so you're asking what is the ratio of effective mass to free electron mass. Okay, this ratio you have to calculate. पहले तो इफेक्टिव मास निकालो. ओके, so calculate effective mass. तो effective mass कितना आएगा? तो h cut square d2e upon dk square. Okay, and you calculate d2e upon dk2. पहले dk कर लेते हैं calculate e by dk. Okay, that will be what? 2a. Okay, 2a k, and then कैसा आएगा ये?
सर निकालना कहाँ पे सर ये?
d2 by dk स्क्वायर आप कैलकुलेट कर जाते हैं ना.
हाँ हाँ,
तो सर
सर निकालना कहाँ पे?
फिर निकालना आपको इफेक्टिव मास वर्सेस एम नॉट का रेशियो निकालना है.
लेकिन सर k भी एक आएगा ना डिनोमिनेटर में. तो सर मतलब k की किस वैल्यू के लिए निकालना है?
आप पहले तो k की किस वैल्यू के लिए, नहीं वैल्यू के लिए क्यों निकालना है? आपको तो सारे कांस्टेंट दे ही रखे हैं ना आपको.
बट सर k नहीं दे सकता, k भी तो आएगा k स्क्वायर आफ्टर डिफरेंशिएशन सर.
अच्छा, तो k का वैल्यू जस्ट लेट मी शो bk स्क्वायर क्या आएगा? श्योर?
हाँ सर.
Yes, sir. But free particle will be when k tends to 0,
No.
right?
So
But m star.
So if you put k is equal to 0 near the band edge, then what will happen? If the question is asked near band edge, k is equal to 0, तब m effect कितना आएगा?
Near
h cut
So
square
near
upon
band
2a
edge
square.
तो pi by a लेना पड़ेगा ना
Yeah,
k
it
की
should be
वैल्यू.
5 by 0.
It should come h cut square to, I'm writing answer, 2a square. ये आ रहा है क्या आपका? अगर मैं k is equal to 0 put कर दूं,
सर
Yes, sir. आ रहा है.
Yes, sir.
so that means this question is asked near the band edge. Near band edge. और वैसे भी आपका near band edge पे
The
ही
bottom of the band edge, right? Bottom.
yes, correct. Near bottom of the band edge. उसी पे वो एक्चुअली फ्री पार्टिकल तो बिहेव करता ही है. ठीक है, सो नाउ कैलकुलेट रेशियो. सो रेशियो आई एम डायरेक्टली राइटिंग आंसर m star upon m naught should come 0.218. 0.218, that is 0.22. ये आना चाहिए आंसर. चेक करो एक बार.
Sir, how to calculate m?
You know p mass भी आपको मास इफेक्टिव मास तो आ गया. अब you know what is h cut. H cut is what? 1.5 1.05 ना, 1.05 to 10 raised to power minus 34. Okay, a value is given, a small a value is given. Okay, and what is mass? m naught is 9.1 to 10 raised to power minus 31 kg.
Oh, it's for electron.
Yes, it's for electron.
Oh, that had to mention.
चेक करो आ रहा है कि जा रहा है. चेक कर लेना, आ जाएगा क्वेश्चन. एग्जाम का आया तो आ ही जाएगा. किसने किया है अभी तक?
हाँ सर, आ रहा है सर.
नाउ ऐसे सारे बैंड थ्योरी में सारे अभी तक जितने भी क्वेश्चंस आए हैं सारे ऐसे इफेक्टिव मास के आए हैं. डिस्पर्सन रिलेशन दे दिया है, इफेक्टिव मास निकाला है या टेंसिव स्ट्रेस निकाला जैसा पहले निकाल रहे थे. सो नाउ एक क्वेश्चन हो रहा है 2018 में गेट 2018 में क्वेश्चन आया है. दे गिवन ई के रिलेशन. ओके, सो दैट इज ई नॉट minus half w cos k. Okay, so where where w and e naught are constants. Okay, they are asking effective mass calculate effective mass, okay, near the bottom of the bandage, okay, near the bottom of band, near bottom of band, okay, that is k is equal to 0 पे आपको to calculate this effective mass.
2h का स्क्वायर बाय ओमेगा स्क्वायर,
W square
तो आंसर दे रखा है 2h का स्क्वायर a स्क्वायर
W
by w, ओके। सो अभी ऐसे क्वेश्चन
sir.
करने से कोई फायदा नहीं, तुम खुद कर ही लोगे, सारे सिंपल क्वेश्चन ही हैं, 2-4 क्वेश्चन और भी 5-6 क्वेश्चन और भी हैं, सारे इफेक्टिव मास के हैं, ओके। सो टुमारो we'll discuss, okay, how can we differentiate between metal, semiconductor and insulator using band theory, okay. So shall I stop this?
Yes sir.
थैंक यू सर।
सर
हाँ बोलिए।
सर बैंड थ्योरी में थोड़ा डाउट आता है सर, मतलब अगर मैं बुक से किसी से रीड करके एक बार देखना चाहूँ तो कहाँ से मैं रीड कर सकता हूँ सर?
अब वो देखो, वो बैंड थ्योरी को बहुत पढ़ना पड़ता है एक्चुअली। अगर आपको बहुत क्लियरिटी चाहिए तो इसकी मैथमेटिक्स में जाना पड़ेगा, ठीक है। वो मैथमेटिक्स में जैसे आपका फ्री इलेक्ट्रॉन मेथड है, और जो आपका टाइट बाइंड है, ये तो बुक्स में दे रखे होते हैं। उसके अलावा भी दो तीन मॉडल और हैं, जीमान मॉडल है, फेमैन मॉडल है, वो सब पढ़ना पड़ता है। वो पढ़ के उसमें से आप पढ़ोगे 8-10 घंटा, फाइनल आंसर निकल के आएगा एक लाइन का, ठीक है। तो वो इतना उतना करने की जरूरत नहीं है, जितना समझ में आ रहा है अभी ना, उतना एग्जाम के लिए उतना ही काफी है। बाकी फिर ग्राफ प्लॉट करना है, वो सब करना, वो सब रिसर्च की चीजें हैं। वो तब ज्यादा क्लियर होगी जब तुम रियली में जाके किसी सॉफ्टवेयर में जाके फंक्शन को प्लॉट करोगे, वैल्यूज दोगे, प्लॉट करोगे, तब वो जितने भी सॉलिड पीस की किताब में ग्राफ बने हुए हैं आपके सॉलिड्स के, डिफरेंट सर्कल इनके बैंड स्ट्रक्चर बने हुए हैं, और ये जो हम कर रहे हैं वो आपको उस समय समझ में आएगा। अभी वो सब क्लियर नहीं होगा, ठीक है।
यस सर।
अभी जितना एग्जाम के लिए पर्पज से सॉल्व नॉलेज चाहिए उतना ही रखो, और अभी ज्यादा कुछ चाहिए भी नहीं है। सिंपल फॉर्मूले चाहिए आपको, डेंसिटी ऑफ स्टेट निकालना आना चाहिए, इफेक्टिव मास निकालना आना चाहिए, डिस्पर्सन दे रखा होगा, ठीक है। थोड़ा बहुत नॉलेज आपको रेसिप्रोकल लेटर्स चाहिए, क्रिस्टल स्ट्रक्चर का नॉलेज चाहिए, कोऑर्डिनेट्स लिखने आने चाहिए क्रिस्टल स्ट्रक्चर में पॉइंट्स के। सो उससे आपके सारे क्वेश्चन बन जाएंगे, ओके। उससे ज्यादा कॉम्प्लेक्स क्वेश्चन बनाना पॉसिबल भी नहीं है, एग्जामिनर के लिए भी पॉसिबल नहीं है, ठीक है।
यस सर।
बाकी ये देखेंगे, कल और डिस्कस करते हैं, कल और परसों में कितना हो पाता है।
ओके ओके सर। यस सर, थैंक यू सर।
थैंक यू सर।